The Hubble Space Telescope is an iconic observatory orbiting at an altitude of 535 kilometers. However, with no onboard propulsion system, uncontrolled re-entry of the Hubble is predicted for the year 2027 with a 1 in 240 risk of human fatality. Hi, my name is Jay and I'll be presenting our design for the safe capture and deorbiting of the Hubble Space Telescope on behalf of our team, Javelin Space Tech. Our team consists of 5 members: Matt, Morgan, Victor, Aaron, and myself. Currently, there exists no solution to deorbiting this Hubble Space Telescope. As the telescope reaches its mission and life, it will deorbit uncontrollably into Earth's atmosphere as it loses altitude. Hence, our primary motivation is to deorbit the telescope in a controlled manner via a capture vehicle. An autonomous berthing and docking sequence of the telescope onto the capture vehicle is proposed using a robotic arm. The docking phase of the mission will incorporate the soft capture mechanism installed on the last servicing mission of the Space Shuttle program. 6 main mission phases are defined for our project. The first phase of the mission is the launch of the capture vehicle into space. The capture vehicle will be launched on board the Falcon 9 as payload and injected into an orbit of altitude 250 kilometers and inclination of 28.4 degrees. Following this, the second phase of the mission is initiated, whereby the capture vehicle begins and approaches the orbit of the telescope at an altitude of 540 kilometers. At the end of this phase, the capture vehicle will rendezvous in close proximity to the telescope. Detection and tracking of the telescope is performed in the next phase to confirm the pose of the telescope and the location of the berthing grapple fixture. The berthing phase is then commenced with the 7 degree of freedom Canadarm2 approaching and berthing with this telescope via the grapple fixture. With the telescope berthed, the docking phase commences using the soft capture mechanism. The final phase of the mission is the controlled deorbit of the capture vehicle with attached telescope back to Earth. The proposed mission has numerous engineering requirements that outline factors that shall or should be satisfied as per the stakeholder needs. A few of the most important requirements are shown. These will be addressed later in demonstration. 3 design alternatives have been considered which satisfy the engineering requirements. The first solution is a net capture system which involves capturing the telescope using a deployable net. The telescope is then brought back to Earth in a controlled deorbit. The second proposed solution involves firing a tethered harpoon at the telescope to penetrate the external surface, whereby the barbed harpoon becomes stuck in the telescope. Similarly, the telescope is brought back to Earth in a controlled deorbit. Finally, the third design alternative transfers the telescope to a graveyard orbit of approximately 36,000 kilometers in altitude, reducing the risk of collisions with operational satellites. While these design solutions satisfy the engineering requirements, we have come to the conclusion that the autonomous docking method is the most suitable solution to satisfy our engineering requirements and stakeholder needs. These components are combined to produce an integrated system that follows a carefully planned system architecture, which describes the interaction between the different subsystems. This provides a feedback loop between the computer vision and the UR5 to successfully perform the autonomous berthing and docking maneuvers. We have implemented a live simulation that emulates the autonomous berthing and docking of the Hubble Space Telescope. This simulation aims to mimic aspects of the real-life mission outlined in the concept of operations. The Canadarm2 is simulated using a 6 degree of freedom UR5 robotic arm. The telescope's soft capture mechanism and grapple fixture is simulated using 3D printed components. Finally, the grapple target is replicated by an AERO3760 fiducial, which is detected using an OpenMV H7 vision system. The final integrated system can be validated by checking the simulation outcomes against the engineering requirements. The OpenMV H7 computer vision system detects the AERO tag using a MicroPython algorithm. An LED turns red if the AERO tag is not in view and green if it is in view. The computer vision algorithm determines the pose of the AERO tag relative to the camera. The UR5 robotic arm then receives a command to move to the correct location towards the AERO tag. The robotic arm is able to move the end effector to any position and any orientation when the AERO tag is in view. The robotic arm is also able to correct itself as the AERO tag moves in real time, making slight adjustments to its position and rotation.